Thanks for John for invitation to share one of my research. Actually, this is ongoing research we're doing collaboratively with Wells Fargo, the banking industry, the model risk team. Actually, the paper has not been submitted. It's going to submit within a couple of weeks. So you are actually the first audience to listen, to give some advice, maybe critical comments to this work. This is the keyword is explainable. So we want to provide a constructive approach to do for that. Okay, for neural network or deep learning in a sense. This is the agenda. So first of all, I will introduce some background of explainable artificial intelligence, in particular like a critical issue of explainability, some existing approaches, and then the new approach we are proposing. Okay, and then we will focus on a particular model called explainable neural network, or in short, XNN. X means the second word in explainable. Okay, EXX. Okay, so we will, in particular, want to describe the architecture from computer science point of view, and then from optimization, we will have a new algorithm to do that. And finally, we have done a lot of simulation study, but I just, for the time constraint, just give one particular study, and also a real application in fintech, actually P2P lending industry. All right, that's a plan. Here, so I think everybody knows deep learning today, right? So deep learning has been so popular, it has a lot of success story. Actually, it does offer many breakthroughs in artificial intelligence. No need to mention AlphaGo or things like that, right? So it's all based on neural network. This has been for many years, but due to the availability of big data, the same topic of this conference, also the computational challenge, which is now solved by both software and hardware. Software in terms of computational algorithms, like a backpropagation by Jeffrey Hinton and his colleagues, and some like first order optimization algorithm like gradient descent, SGD. Batch normalization, as well as something called like ADAM, which is adaptive stochastic optimization. So which is a very smart way to tune the learning rate. This is, and also hardware like GPU, right, and TPU from Google as well. So all of these put together, so we have the new momentum, the new success of a neural network. But neural network is highly complicated, and it's often referred as black box. Okay, that's actually cause a problem. So it has high prediction accuracy, which is true, high performance. But as critical, the issue is interpretability, because we don't even know. Even the model developers themselves, they don't understand why the model works. Okay, so for example, in here, this example, like a mini data set, like a small image. Then it's just a 3-layer with like convolutional and pooling, so on and so forth. Then with a softmax from the digit 0 to 9, 10 classes. It can predict pretty well, like 98 and 99% of accuracy. But we do not really understand why that can happen. Okay, so we need to understand both like how transparent the model it is, and also how can we explain it. Okay, that's the issue I want to address. And I recently, actually last year, United States Defense Advanced Research Project Agency called DARPA. DARPA has actually initiated a new program called XAI for defense purpose. Okay? They want to try military purpose. They want to understand why those kind of models or artificial intelligence the algorithms really work, for what reasons. Okay, they actually do a summary in a slide. Gani, he is the director for this program. He has this chart. So this is an incomplete list of many of those machine learning algorithms. That means there are quite a lot, but it's not complete, right? But here that we see the deep learning here, it has like the y-axis is accuracy. It is highly accurate, but in terms of explainability, it is a minimal. It has minimal explainability. On the other hand, like decision tree is just like you have like x1 variable, one of x, it cut it left and right, right? and then you keep cutting that recursively. So you actually understand which variable is cutting and at what split point. So that can be actually transparent and explainable. But unfortunately, compared to deep learning, it's not as accurate as possible as deep learning. Also, it's not as good as random forest. But random forest is an example of many different trees. Usually start with 500 trees put together. It performs really good. Yeah, actually, it's like a winner program algorithm in Kaggle competitions. But when 500 decision trees, each of the trees is explainable. But when 500 then put together, it becomes like a black box. Okay, so let's say random forest is in here. So it's the second one, like a highly accurate, but also the second one least explainable. This is a trade-off. All right. So the purpose of what we're doing is actually want to maintain the high performance on the y-axis, but on the other hand, we want to move this kind of points to the right-hand side. Try to increase its explainability. That's the purpose of the study. All right. So actually, this is a recent article in risk.net in banking industry, because this is a collaboration with Wells Fargo. There has an article titled "Machine Learning Hits Like Explainative Barrier." Actually, Federal Reserve in the United States, actually they want to regulate the use of AI, black box models, unless the model is explainable, can be made transparent. All right, so this is actually a hot topic these days. Actually, Vijay Nair, he is my PhD advisor back to University of Michigan in statistics department. Now after retired, he's working in Wells Fargo. He had a statement, people think that because the results come from complex computer algorithms, which is powerful, okay? So they don't have to think a lot of, think care of why it works, so they can just trust them. But in reality, the opposite is true. What does that mean? That means the model, if you don't understand, you just take it for granted, use it blindly. That's very risky and highly dangerous, because nobody will tell what black swan event may happen tomorrow or in the future. All right, that's very highly dangerous. So the problems that can arise if you use them blindly. Actually, a lot of things happening, like including 2008, like a subprime crisis, like the use of CDO models without understanding the model assumption, and so on and so forth. That's all about the model risk. Okay. So to explain some of the models, actually there has been some work done in recent years. Actually, it's a hot topic today, either called XAI, explainable AI, or it is also referred to interpretable machine learning, IML. Okay, quite some people are studying, working in these directions, including myself. And there are two approaches I listed here. One is the model agnostic approach. It doesn't matter which model you're using, just like whatever black model you have. You just do some kind of sensitivity analysis or diagnostic analysis. For example, you have y on the right-hand side, you have different x. They just take the derivative of each y against each x to see how sensitive for this particular input. All right, so this is like the idea. So either do it globally or locally. Actually, Jerry Friedman from Stanford, a statistics professor, I guess in JAWS or Annals, he have a paper published on talking about the partial dependence plot, which is the first one, I guess, in this approach. And also ICE is individual conditional expectation, also treating each main fact separately. And also ALE method, Lime method, K-Lime. Lime is one of the most popular methods today used. Actually, a lot of packages either in Python or R actually developed based on this technique. And also, this is also the Wells Fargo team did, my colleagues. So, my collaborators accumulated to the derivative effect plot, also doing it this way. Okay, this is basically, it does the job for all kinds of models. Whatever model you have, no matter how complicated it is, you just treat the y and x. You do not consider what's happening in the middle. You just have the input and output. Then you try to analyze what's the sensitivity of each x or each pair of sensitivity, which is interaction effect. All right. So this is the idea. So the other approach is called the model distillation approach, and I think this has a little bit similarity to my previous talk, which is talking about surrogate model, right, Kriging. computer experiment, we have done a lot of things like that, spatial statistics, right? So, which actually provide a surrogate model. This is the same idea. The original model may be very highly complex, like deeper neural network, but it can be approximated by a distilled, a smaller but a faster surrogate model. And that kind of simple model is easier to be explained. So that's the idea, right? So Jeffrey Hinton, and this is Jeff Dean from Google. They actually done some work, highly cited work for so-called distilled neural network. And then the other group is from Microsoft. Corona and his collaborators has done a series of papers called model compression or model distillation. Basically, you have a large model, then you compress it to a small model, or distill it to a simpler model, right? Then you try to explain it. And also my collaborators from West Fargo, they have recently published another paper called tree partition and lime soup. Basically like a lime, but it's a supervised fashion with some tree partition. Basically, you have the complicated model. You cut it to different sub-models, and each model is explainable, and put them together, it's still as a proxy of explainability. Okay, that's the idea. This is two approach, but you see the original formulation is also based on the complicated model. Then try to either find a diagnostics approach or find a simpler proxy or representative. That's the idea. But actually, back to statistics. As a statistician, we know we have so many models in statistics which are fundamentally or intrinsically interpretable. For example, linear model, right? Linear regression. It's very easy to explain because we have x, y equal to linear combination of many x. So we can see the different main effects of interaction effects. Or logistic regression by some sort of like transformation. Generalized additive model. Each model can be a curve. Put them together additively. Right, so this is also popularly used in statistics, and a decision tree, as I mentioned. Each decision tree is easy to interpret. So this, so on and so forth. There's actually many models in statistics. They don't have the problem with explainability. But why? What's the problem here? The point is here. These models are too restricted for complex data. But now we have a big data, right? The data is complex. It turns out these models are too much simplified to model such a complex behavior, right? So especially if we compare these models with black box type of models like machine learning algorithms, like a support vector machine, SVM, right? Especially we have a kernel, right? Kernel mapping to high dimensional. With a kernel trick, we don't even have to worry about what's the mapping explicitly. But that's a danger because we don't understand what's the mapping. We cannot explain it. Right? So SVM is highly predictive, but it's hardly explainable. Random forest, as mentioned, put them example, lots together. It's like a messy black box and a DNA neural networks. Okay. So in this paper, in this project, our goal is to design. Also want to do complex models, but at the same time, we design such models that are fundamentally explainable. So as the title indicated, we use neural network. Neural network, by nature, it's a very complicated, but can we do it differently such that it has some interpretation fundamentally, all right? So that's the idea. So actually, recently a paper published by my collaborators from West Fargo, like Vijay Nair and other colleagues, they call the explainable neural network based on additive index model. Additive index is like a projection pursuit, rather than using GAM model, GAM which is general additive. But now each additive is a function of linear combination of many variables. All right, that's the idea. So projection, you do projection first, and like principal component analysis, each projection, then you treat that principal component as a variable, and with a function on it, then put them together additively. So that's the additive index model. All right, so actually this just published this October of this year. But this is not an academic journal, all right? It's like a magazine in the banking industry. It's a popular one. But then we take it back to do some theoretical study, and realize this is architecture. So this is the idea. Like we have x1 to xd high dimensional. It could be. Then each projection is just a linear combination. Like you can think of this as a PC1, PC2, PC3, right? And you have this kind of components, these projected data. For each one, it's one-dimensional, unidimensional. Then you just use a non-parametric. For example, smooth spline or regression spline, whatever, right? But the problem with smooth spline, then the statisticians usually have to do something called backfitting. You have to estimate them iteratively. Estimate one, then estimate another, so on and so forth. But which is very time-consuming. Oh, sorry. So then it turns out, if we treat it as this structure, because this is just a linear composite of linear combinations with activation functions, right? Then we can take the advantage of BP, so-called backpropagation by Jeffrey Hinton, deep learning. Then we can estimate them, all of them simultaneously. All right, this is like one of the novelty of the paper. So then just estimate them. They have the Y output at the end. This idea. So this is actually the additive. Each layer, each sublayer is a subnetwork. It's a unidimensional non-parametric co-fitting. And then at the same time has to estimate the projection weights. So put them together, just use BP first order methods, which is easy to do, right? Implement it today easily in Python or other language. All right, so this is like just publish it. But it turns out, when I take this model, because they asked me to investigate, is this really legitimate, statistically sound? I found some problem. In particular, three drawbacks I realized from this model. First of all, the sparsity. Yeah, because this is high dimensional, and they actually originally put some sparsity. In order to do the sparsity in here, just do L1 shrinkage, which is very easy to do, like lasso. Here also they also do a lasso in here, but turns out when they have to do this, they have a split this parameter to have additional scale outside. But this turns out they have actually created redundant degrees of freedom. All right, so this is done in the wrong way. So we have to do some normalization before you have this kind of extra degree of freedom to perform L1. So we actually realize the batch normalization in deep learning is perfectly suitable for this case. We just solve it very quickly. And then another one is like projection. Originally, this projection, like PCA, we assume this projection have to be orthogonal, uncorrelated, right? But in this additive model or projection pursuit, it does not assume orthogonal because it's very hard to do. So they didn't do this. All right. So, but in that case, the result turns out can be correlated. But correlated projection, it's very hard to explain. All right. So we have to consider. Sorry, I'm not very good at this project. Okay, should be the next one. Okay. So orthogonal projection. So we have sparse orthogonal. Also, the functional approximation by neural network can be overfitting. Overfitting means it can be highly oscillating, has some wiggles, fluctuations, which is something we do not want to see. All right, so then we can have this kind of smooth functional approximation to prevent overfitted wiggles. So we have these three things, SOS. Okay, it seems like they'll ask me for rescue. So I proposed a new architecture called SOS XNA, integrating those three constraints. Okay, the first constraint is sparse. So we put a sparsity in here. What we have to do is put a normalization, batch normalization, because we're doing batch processing, mini batch. So this N means normalization, something added. For the purpose of orthogonal, we have assumed this projection index to be orthogonal. As you know, this is a hard constraint. It corresponds to Stifel manifold. It's a manifold constraint. Right, so then we solved it with some kind of like updating scheme on Stifel, and also smooth. Smooth, then we have to add something in here, omega. Omega is from here, from the input to the output. We add omega, which is a roughness penalty. Basically, it's an integrated version of squared second order derivative. We want to minimize the curvature, right, to make it smooth. So by these three put together, we have the new architecture. Just outline like this. Then to solve this, we actually propose a so-called SOS BP algorithm because we use backpropagation. And the goodness of this BP is in most of computational platforms like TensorFlow or PyTorch, they have a particularly new function or technology which is called auto differentiation. No matter how complicated your objective function it is, or error function or loss function is, it can automatically differentiate. It's not an approximation. It's exact evaluation by using this kind of chain rule, BP. All right. So we actually developed this, but as you can see, we have a lot of so-called hyperparameter because we want to control the sparsity, we want to control the smoothness. These are all software regularization. So we have quite some hyperparameter. So we have to use random search. We have more than 6, okay, like compared to the previous one. So we actually use random search, but at the same time, we're doing something called automated machine learning, AutoML. So we can actually deal with this. But basically, you have to use validation or cross-validation as an objective function, run multiple times for different combination of this kind of hyperparameter. Then you find the best one. Okay, this is a black box optimization or so-called global optimization problem. All right, but in here, to deal with the manifold, still for manifold, we actually use the Cayley transform from the differential geometry. Then we actually have updated to guarantee the orthogonality during each step of updating. Then other than this W parameter, which is projection weights, other parameter, unknown parameters just updated by SGD. And you can see here, this is a first order method without computing the Hessian matrix, because that will be second order, highly slow, right? Very slow. So we use the first order, and then here we use ADAM, adaptive stochastic optimization, to do that. Then we just do the mini batch. There's a big data. We have to make it scalable. So we cannot put all the data into the machine. We have to do batch by batch. All right? Then we have to do like a number of approach to control, because the server not always work for us. So we have to, do the budget control. Say we want to make it 10 approaches or 100 approaches. It depends how long we can use the server. Because the server now in the department is highly used by many different colleagues in my department. All right, so that's the idea. So here, this is the algorithm. It's a highly intensive algorithm, but actually it can guarantee the convergence because due to the SGD. Also, the Cayley transformation, when the tau parameter is small enough, it's also guaranteed to have a gradient descent. Okay. So numerical examples. Let me give you 2. One is a simulation. One is a real study. Here it is. Okay. So this we assume underlying model like as complicated as this, right? We basically we have high dimensional. Here is 10-dimensional, x1 to x10. Then we have the one-dimensional output response, and the x variable here made correlated. So we have the correlation like 50% of correlation coefficient between every pair. Then we just plug these variables 10-dimensional to this additive index model. This is additive. Each one is a function like different shape. Okay, and this is the weights. The weights you can see here. Actually, we have 10-dimensional, but the last 3 purposefully we make it as a noise parameter, which is like to take care of the sparsity. Sometimes we can do automatic variable selection. And this is the underlying choose, DGM, data generating mechanism, right? So we have the first ridge function, so called like H1, H2, H3, H4. They all have different shape. And each function is a function of a projected data. That's projected, the first one, just the first variable itself. The second is the second variable. But third one is a combination of x5, 6, 7. H4 is H3 and 4. Right? It can be very flexible. The model can be highly complicated. This is a scenario for DGM, but on ground truth, so-called ground truth. Now, our purpose is let's try different algorithm. Okay, some black box, some easy model, some expandable model, and including the one we proposed. And these are the results. All right, so we actually try this with different sample size for 500, 1,000, 2,000, and 4,000, and so on and so forth. We try that. Right? The idea is just like we have the data simulated, so we take the data to train the algorithm, but because we also have hyperparameter to determine, so we actually use either cross-validation. In here we use validation, a separate validation data set, because we have the generating mechanism. We can generate no matter how many data we want. Then we can use this to determine this, and turns out this is a training error. Because we use the hyperparameter, we can train this, it's more or less around the noise level. But turns out the random forest is very easily to overfitting. Because it has a MSE even smaller than original, expected error, which is because we use the standard normal to simulate the noise. And this is overfitting because the noise is even smaller. It's fitting that noise, random forest, all right? But it turns out when we test it on the test data, because that's really something we want, right? We want to test it on unknown data rather than the training data. Right? We test it, and it turns out, as sample size goes, this algorithm perform better and better. Random forest is the worst case. Okay? And the red one is the one we propose. It's called SOS XNN. And also without SOS is the XNN, so which is in here. And SVM is somewhere in the middle. Here is performed pretty good, but here is not the best. Right? Also another one is a sparse additive model. So we actually compare quite some models and find okay, it has the new proposed method has the best performance. Okay, overall. And then let's check for this kind of prediction performance. As we know, like SOS XNA itself is fundamentally explainable because we can explain from the projection point of view, from the ridge function point of view. Right? But let's say the estimates. The estimates may not be exactly the same as like a true model because that's a really challenging task. It's a very complicated model. It's very hard to find exactly the same thing. But the result we find, because we do Monte Carlo replicate, so we just take a random one from it. The first one, this is ground truth. This is the estimates. The first one is almost the same. Second one is fitted by the third one because we have the rank order. All right, and here is also captured, but not exactly with the same projection index because here has a little bit. Sorry. In here, it's not the same as here, but you can see the variable, the variable is captured, but the last one, which is not quite true, right? So basically, the model we fit it from this kind of architecture, not guaranteed to be exactly the same as the underlying truth, but nobody knows the ground truth, right? If we have facing real data, so actually, this result is pretty reasonable. Then we apply this to a real data set without ground truth. We don't know what's ground truth. And this is like a so-called P2P lending. Actually, in the United States, one of the most popular P2P business is called Lending Club, LLC. It's listed in NASDAQ, I guess. Yeah, but the same story does not have apply to China because China has a lot of problems with P2P. But anyway, but we use this data. It's more trustworthy. So all the data are available since many years ago, but we just consider the time frame starting from 2015, the January, to June of this year. And also the risk, it has many variables. You know, we pick the variables, for example, the risk score is like a FICO, like credit score. Like basically, we apply mortgage or credit card. This is the most important indicator, whether you will be granted or declined. All right, so risk score. So risk score we truncated it to be 600 to 850. The reason we do this is because everybody below 600, they will automatically get disapproved because that's too low in terms of credit score. All right, so we just take this 600, and also we have the variable like debt to income ratio, like financial burden, and also the employment length for applicant. Right, applicant also like how much the money is applied, like amount requested, and as well as application date because it's over time series, right? And also where each applicant is made, it also has to declare the purpose of the loan. For example, they want to do a debit consolidation for credit card financing and for housing purpose, for purchase and others. All right, this is an aggregated purpose. Originally it has more than 10 and 12, so we just aggregated to 5. And this is the result, ROC, like AUC, you know, where it's one of popular measurement to assess the predicting accuracy. So we split the data into 40%, 10%, and 50%. 40 for training and 10% for tuning hyperparameter. And then resulting model is tested on the 50% unknown data. All right? So then we just compare the accuracy and realized SOS is not the best. Okay, the best one here is a random forest, the green one. And the worst one is actually logistic regression, because logistic regression is too simple to capture the complexity. The random forest in here it does perform the best. But the problem is it cannot be used because it's like a black box. All right? So and on the other hand, if we compare also MLP like a deep learning with multiple layer perception, and XN is also similar to SOS, but it's not as same interpretable because we have additional considerations. It turns out that 97.57% is close, to the best model. But as a reward, we have explainability. Okay, so this model would be highly, I think, I recommend it if you compare with random forest, because random forest is a black box. And then also let's check the results. The results turns out this is like first ridge function versus like X3 risk score. When it's small, it does not disprove. When it goes to beyond the threshold, it's automatically granted. So actually, I think in the acquisition stage, learning club, they just do simple, like yes or no. All right. If it's below certain threshold, it's no. After, if it's beyond, then it's okay. But when it's being very high, it has some decline. That's interesting. It turns out that when we see the real data, this is a risk score. It does when has this kind of pattern. Small is like a zero acceptance, approval, then decrease a little bit. So this may depend on the company have some strategic acquisition like a strategy. Sometimes they want to focus on a particular segment of data customers rather than all the customers. Some highly like credential people, they may not really need this kind of internet financing. Maybe they have other channels to get the money loan, right? So that's the real data. So we actually can capture this kind of curve in a smooth way in here. And also others as well, like employment length and so on and so forth. Basically, the fitted results from this SON can be explained in a sense versus this real data. All right, so I think I will stop here. Let's see if you have any questions. Also, this work is ongoing, so actually we're doing something more in terms of improvement. Thank you. Yeah, question.
So the number of range functions, is that, do you use that as the tuning parameter, or in both of the first simulation you just set it at 4, which is exactly the model you're using the data?
Right. We do not set it 4. Actually, we set it to be about 10. Because the maximum simulation, right? Simulation, we set it as 10, but it turns out final result turns out to be 4 because we apply the L1 shrinkage. The shrink from 10 to 4. Okay. Yeah, this is This is actually by hyperparameter selection because we have a lambda to control that. Yeah, but it's a hyperparameter. You're right.
Okay. So second question, in the example, the real life example.
Okay.
So seems like the ridge functions can be, if you go to the plot, next one.
Okay.
So like each of the ridge functions sort of associated with one variable, right? So the right side is the
one way right.
variable shows to be significant.
You're right. Yeah.
Okay. So that's sort of say why. Could you just fix
That's actually one of the remarkable results we have. We started with an index model, which can have different projection. Like here, we have small projection in here, right? But it turns out actually it tends to be a single variable included. So this is actually called a GAM model, generalized additive model. Yeah. Additive model without many like other variables involved. This model is actually is better to be explained. So, but now we're still curious to investigate why this could happen. This kind of model is more preferred than other models. So this is the result from the algorithm. So the algorithm it can either choose a complicated model with multiple projection or a simple model like GAM. And turns out GAM is recommended. That's actually one of the remarkable property of the model. We're still trying to understand why this is happening.
But it's just for this particular case.
For this particular, actually the same thing as happens for other as well. If you see in here, you see this is tend to be more like just a single variable, unless it's really needed, right? And this is actually one of the reasons is because we have the sparsity parameter for controlling the projection weights. When we make it very sparse, it'll be like each like just one variable included. And this is a very extreme case of orthogonal because every body itself is orthogonal with another variable itself. All right. So this is actually one of the remarkable properties we are still investigating. Yeah. Thank you for the very, very good question.
Okay. So thank you again.
Thank you.